Hello, this is Paul from Tech. In this video, let's prove Theorem 1.7.1, the second part, prove properties of triangular matrices. See, triangular matrix is invertible, equivalent to the diagonal entries all zero. Okay, let me introduce a direct proof. In the future, we have another proof use determinant. Okay, so I just give example. A small 3x3 matrix to give you the idea what we can prove. Okay, so let's pick a lower triangular matrix 3x3 as example. And this, if this is invertible, we need to say, okay, so the diagonal entry are non-zero and the backwards are the same. How do you say, if this is invertible, how do you say the diagonal entry are non-zero? We have to use this. Okay, so this result, invertible, a matrix is invertible, equivalent to the reduced row echelon. Okay, is identity. Okay, and that's equivalence theorem we learned before. Equivalence theorem. Okay, we already have this result. How to use? So reduce the row echelon, we have to do row operation. We just do row operation. See, step by step. Let's do this. The first, I look at the first number. Okay, A11. A11 should be not zero. Okay, see, I can get a result now. I know A11 is not zero. Okay, why? Otherwise, the first row all zero, and then the reduced row echelon will not be identity, right? And this is the first step. Okay, so I know this is not zero, and I want to get a reduced row echelon. How to do? I will make this 2 0. That's easy. Okay, so we can do this one. I do the second type of row operation. See, I can make now. I know. So let me make a A11 into 1 first. And then go here. So how did we get? We do a symbol, just multiply the first row, okay, by 1 out of A11, right? Because the A11 is not 0, therefore I can definitely make this into 1. Did the first step, and then now I need to make this 0. Okay, so I can use the first row, use the third type of row operation. Okay, make this 0, this 0. That should be easy, right? Okay, so I directly get it. Okay, go to here. I make this 0. I use the third type row operation. The third type. Okay. Why here we keep the same A22? Why we will not change? Imagine the first row multiply negative A21. We only change this. We will not change this because 0 there. Imagine. Okay, so this is not change. And another type get this 0, this also not change. Okay, so now we look at it, this number. Okay, and we know this time A22 should be not 0, right? Therefore, we get it again. A22 is not 0. Okay, the same. Otherwise, we have the second row all 0. So the reduced row echelon is not identity, right? Okay, again. If this is not 0, I can make this as 1, which is leading 1. I can do this first type of row operation. Okay, let me put here. Okay, so how did we get this? Is multiply row 2 by this. Okay. What do we do? So now we can make A32 into 0, and then again by the third type of row operation, right? So let me put. Okay, so this is the third type of row operation. And now, can we look at again, this 833 keep it the same because the third type will not change 833 because here is 0. Okay, so that's the major. When we keep 833 here, so we need to 833 be non-zero, otherwise the last row is 0. Okay, so the same idea now we have 833 is not a 0. So do one more type of row operation, right? The first type multiply the third row by. So let me just put it here, the last step. Okay, see, this is the identity. Okay, so therefore, so we get it so far is all the diagonal entry A11 is not a 0, A22 is not a 0, A33 are not a 0. Okay, and then another is backwards. If we go backwards, if all the diagonal entries are not 0, see, so we can follow the same way. And to get the reduced row echelon is identity. Therefore, A is invertible. So that's the proof for the first. And then look at the second. The inverse of an invertible. Okay, well, look at the inverse of an invertible lower triangular is a lower triangular, and the same, the inverse of an up is a up. Okay, if they are invertible. So how do you say? So how do you prove this? We can just prove the first. Okay, the lower triangular, and we can make another way, arrange another way to get the upper triangular for you. So what is a lower triangular? Look at the inverse. Okay, so I just take example. So this is 3 by 3 invertible lower triangular matrix. So therefore the diagonal entry is non-zero, right? We need to find the inverse. How to find the inverse? We have to use the inversion algorithm. See, inversion algorithm, let me put here. Okay, so inversion algorithm means we have to do row operation to make A into I. I reduce the row echelon as I, and then I will go to the inverse. So we follow the inversion algorithm. Now, to work on this matrix, the first, what do we do? We have to make this 1. Okay, easy. Oops. Let me put I. Okay, so let me put I. Inversion algorithm. Okay, so the first is A, and then I, we have to make A into I identity. So we work on this first. We do this row operation. Multiply R1 by A11, right? Okay, therefore this is 1. And here we will change. See, what do I get? I get this matrix. And the A11 is non-zero, so this is a number. So good, I find it first. And then the second step, I make this 2, 0. I just by the third type of row operation. Okay. Yeah, is this true? It is. I use the first row, multiply number, add to the second row, add to the third row, make this 2, 0. And they see very good pattern. and this number will no change. 822 was still here, and all the 832 and 833 are all here because these two are 0 on the first row. Okay, and again, so this 0 will change because so the first and here the entry is not 0. I use the star to describe a non-zero number. Okay, so whatever. So let me describe this is a non-zero number. 0 numbers. Okay. So here's another number, and again this 1 and the 1 still keep the same because the same reason the top 2 zeros. Okay, we will not change. Yes. Now almost. We look at this 82 is not a 0, right? So I can make this into 1. How? Okay, I do this row operation. Okay, I get this. Is this true? Of course, the third row I will not change. I change the second row. So here is 1, so 1 over 82, which is the inverse of 82. So now, you get it? Okay, almost right. I make this 0. I do this operation. Okay, see, so the third type of row operation, use the second row, I can make this 0. Okay, the same reason I keep 833 the same. I keep this 1 the same because here is 0, here is 0. Okay, will not change these two values. Here's the star because the probably is a non-zero. I don't care about this. Okay, and then the last step. Okay, see, and this time here is I identity. So this matrix should be the inverse of A, right? And we'll look at it. And what this is a lower triangle. And also we have a pattern. You see, what is the inverse? What is the diagonal entry on the inverse? And the pattern is like this: the inverse of each diagonal entry from the original matrix. So this is a simple idea. Okay, we using algorithm. We can see. Okay, we can see a lower triangular invertible matrix has the inverse. They have the same type of inverse, which is lower triangular. How about the up? Let me show you the up. Okay, if A is a square, is an up triangular, what is the inverse will look like? Can we see? I can do here. Okay, so I just make the transpose of a transpose equals the original. In this way, what do we have? We will have what is matrix? Okay, we have the result for upper triangular. Okay, transpose you get the lower. So this is a lower. And then we have a property to use. Okay, see, I can switch the order of operation of the transpose and this inverse. Okay, similar like a power rule. Okay, that's a property we learned before. So now we definitely have something. This is a lower. Okay, and we already proved the inverse of a lower is a lower, right? So I get it here is a lower triangular. And therefore, the transpose of a lower triangular is what? Is an upper triangular. So you know now, definitely. And this is upper triangular. Okay. And therefore, the inverse of upper is up. Okay, that's the proof. Thank you.